Hello. Today I'm going to review for like everything we have done in this semester for the final exam. So I designed this basically to make questions for the final exam myself, and then also I hope this helps you prepare for the final exam, right? So okay, let me start. The final exam is Saturday, May 4th, 10:30 to 12:30, 2 hours at the same classroom. And it's open book, open note, whatever is allowed, like any references are allowed except for two types. One is a human, you cannot bring someone else. Also, what is not allowed is internet, right? I don't want you to search on internet, so your cell phones are not allowed during the exam. But you can bring a calculator. Calculator uh, is okay, but as you saw from the exam, like so from the during the semester, you don't have anything special. So at most you can use calculator to add and multiply things. That's all. So you just need a basic calculator with four functions, right? Addition, subtraction, multiplication, division is enough, right? And in case if you forget or if you don't have a calculator, I will let you use my own cell phone, but like not throughout the not throughout the exam, but for a few minutes, right? Uh, there may be a few questions, like for example, predict something based on regression table. Then you need to multiply and add things, or you may need to calculate the t statistic, which requires division. So for these basic things, you can use a calculator. Okay, and I posted past exams that is available to me on Brightspace, right? So I said it like to find out what's relevant. I checked my records and my files, and I found that this is my third time teaching 420 in over 11 years. And so I uploaded all three past exams. Some of them may not help. So like coverages are different and programs are different, and yeah, and I change it. I change it too. And so I found some relevant questions from another course I teach. So I listed the questions you may want to try. So check on Brightspace. And also in the final exam, it's short answer questions, and you can see from the past exams. So as you can tell from there, it's pretty straightforward, I believe. Like, so if your answer is too long, that means something is not quite right, right? Okay, and then let me start review. So overview, like kind of review of overview, overreview. We have covered these chapters. First two chapters, we spent quite a lot of time on the first two chapters to review statistics, right? Like I defined very, boring things like probability expectation, test, and you don't need to worry about them for the final exam. And the first, and then four chapters, chapter 4, 5 are linear regression with one regressor, and 6, 7 are multiple regressors. Basically, these four chapters are the main chapters. So we set up a lot of basics like how to interpret what is in the setup the model, make assumptions, what kind of assumptions are needed, and how to do hypothesis testing. And we defined like a standard error of the regression, R squared. There was like hypothesis testing, confidence interval, like F statistic, like t-test, p-value, statistical significance. Those basics are literally basic, very basic terminologies and techniques for any kind of regression. So we just consider them in a linear model. So they're important. You don't need to know, you don't need to memorize every single details from here. Later in this review, I'm going to review them, point out what you need to pay more attention to when you prepare for the final. And then these four chapters are basically more practical and more like kind of applicable stuffs like nonlinear regression, panel data regression, binary dependent variable regression, instrumental variable regression. These are specific to the data structure or certain aspects of the data. So they are different. You may combine them. Like for example, you may think about panel data with nonlinear regression, or you may think about binary dependent variable with instrumental variable. Those are possible. So they are more specific topics, which is important, right? So my guide is you may spend more time on these things, and also these four chapters are quite technical, but you don't need to uh, worry much about mathematics or formulas. Anyhow, it is open book, right? So you don't need to worry too much about memorization or memorizing things or the derivation of mathematical equations. Just um, just try to focus on the key ideas. So the first four chapters, the basic regression chapters, covers a lot of things. Estimation of coefficients, which is just ordinary least squares method. Measures of fit, which include R square, standard error of the regression. And then we discuss required assumptions. And also we learn like normal distribution things, some additional things we learned here. And so chapter 4 is about single regressor, 6 is about uh, multiple regressors, and chapter 5 and 7 are more like hypothesis testing, and which is directly related to statistical significance. So various type of hypothesis testing is available, but I will focus more on statistical significance, right? We learned statistical significance as a specific testing result, okay? And then we learned different issues related to standard error calculation, like heteroscedasticity, but it's like more like software. Your program will handle this automatically, so you don't need to worry too much about that. Confidence interval is not easy to learn when you have multiple regressors, like not easy to present and derive. So more important is hypothesis testing here. And here, uh, like I believe if you have a textbook or note, these things will be straightforward, just basic ideas and basic definitions would be enough. So here, more important thing here is like you should be able to read the regression table, the results, and predict outcome. This is the starting point, right? Like if I give you the results table, output table from a regression, you should be able to interpret what is going on and should be able to predict the outcome. That is really the basic. And then you should be able to tell which variables are statistically significant. I'll give you significance level, typically 5%, but 1% or 10% may be used. And given the significance level, you should be able to tell which is statistically significant. And also another important question, especially in economics, is omitted variable bias, right? So think about omitted variable bias and when it matters and what kind of problem it causes, like what is the sign of the bias, right? For example, let me give you a more detailed example. So this is a table, like regression result table, and say that our example in class, student to teacher ratio, percentage of English learners, intercept, and coefficient estimates are given in the first column, standard errors in the second column, t statistics third column, p-value there. And then of course you should interpret this, right? So this means one unit increase in student to teacher ratio decreases the outcome, which is the test score, by 0.1 because it's minus, decrease by 1.1, excuse me, right? But that means when PL is held constant. So everything else being the same, if student to teacher ratio increases, test score will decrease by this much, right? That is the direct interpretation of this number. And then combining all the coefficient estimates, you can calculate the predicted test score. For example, you need specific values, like suppose that student to teacher ratio is 20 and percentage of English learner is 10%. Given these two numbers, you can just plug in those two numbers, multiply them to here 20, 10, and summation, right? If you add all these things, then you are going to get predicted y hat. Right? That is the prediction, which is pretty simple, and you need a calculator to do this. So, frankly, you can do it without a calculator, but just to make sure, you will need one. And the p-value is related to statistical significance. Simply speaking, the smaller the p-value is, the more statistical significant, right? Right. That is the key idea of statistical significance hypothesis testing, and especially when you have a cutoff at 5% significance level. If it is smaller than 5%, 0.05, then we say, like the coefficient is statistically significant at 5%. In this example, there are two variables. Intercept is usually not considered as an important part. So if you think about these two variables, both are smaller than 5%. This is like 1.1%. This is 0%. So both are small enough to say that statistically significant at 5%. But this one, student to teacher ratios, p-value is 1.1%, which is greater than 1%. So you say it is not significant at 1%. That's how you interpret the statistical significance based on p-value, right? And t-statistic is basically some transformation of the p-value. As a rule of thumb, 5% p-value is equivalent to plus minus 1.96. So the larger the t-statistic, I mean, when I say the larger the absolute value of the t-statistic, the more statistical significance, right? And outside of plus minus 1.96, it is statistically significant at 5%. Yes, 2.5 is greater than 1.9, so it is outside. And this is really, really strongly significant, right? T-stat is 10 times larger than TDR, STR, so super strong, right? Very significant. So you may use this or this to calculate, to tell statistical significance. By the way, the t-statistic is calculated as coefficient divided by standard rate error. So these two will give you the t-statistic. Even if I don't give you these columns, still you should be able to calculate that based on these two things. Okay. And omitted variable bias. And in this regression, let's think about the validity of this regression. Then you need to think about any missing important variables, such as family income, right? For example, we know that it is really important in determining the test score and student-to-teacher ratio, but suppose it is not observed. Then what happened? You can think about the relationship with the outcome. So the more family income, average family income in a school district, and obviously test score will increase. And the more the family income is, the better. Excuse me. So it's negative. Should be negative. I mean, the more family income, then the better teaching quality is, right? Student to teacher ratio will be lower. So I'm sorry about that. It should be negative. Then suppose that it may look like when student to teacher ratio is low, then test score is high. That is because of family income, but because as we do not observe family income, it may look like lower student to teacher ratio implies test score, even if it doesn't. Even if this lower student teacher ratio is only due to family income, and high test score is only due to high family income, still it may look like a bias, as if student to teacher ratio causes test score. So that is a bias. Even if there is no direct causation, still there is another link that you don't observe that may uh, mask the estimate. It may look like there is a relationship. So, and technically speaking, theoretically speaking, this omitted variable will fail the assumption that the regressor X uncorrelated with the error term U, right? So we have to check this. So this is theoretical analysis, what kind of problem the omitted variable can cause, the correlation, right? So then you should be able to guess the sign of the bias. So if I suggest a omitted variable like this, then you have to imagine what kind of bias it will imply, like underestimation or overestimation in beta, or like plus side or minus side, which direction the estimator will be biased. Okay, that was the basic uh, regression chapter. Now let's go to nonlinear regression. In nonlinear regression, the main theme is we are like in regression we are interested in the effect of x1, right? Effect of x on y, but the effect may differ across observations. In the linear regression, in the standard linear regression, we assume that the effect is simply beta for everyone in any case, but that is very restrictive. So we relax that. Linear model is relaxed to quadratic regression, quadratic function, or logarithm. Log transformation is taken, or we allow interactions across variables. Okay, and again, the key idea is the marginal effect. So the idea is similar. I'll give you the regression results based on one of these three, and then you should be able to calculate the marginal effect. It is not that difficult. Okay, so let's think about one by one. Marginal effect when you have quadratic function. So this is the quadratic term x squared. When you have x squared, basically the marginal effect you are calculating is this derivative, right? So you know how to differentiate quadratic function, right? It goes away and you delete 1 here, and 2 comes in front of beta 2. So your derivative is the whole thing, not just beta 1. If there was no quadratic function, it will be simply beta 1. But now because of the quadratic part, you get something else. So this part captures the change in marginal effects as x changes, like diminishing marginal returns, something like that, right? As x increases, the effect of x itself may increase or decrease. So that is quadratic function. Log case. Log is a little more tricky because the key idea is log transformation allows you to interpret it as a percentage change, right? A unit increase in log of x implies is equivalent to 100% increase in x. So when x doubles, log of x will increase by 1, right? Conceptually, approximately. And in other words, so if log of x increases by 0.01, that implies 1% increase in x, right? So when x increases by 1%, log of x will increase by 0.01. So log is basically percentage change, right? Approximately. And then you can think about 3 different combinations, right? When x is logged or y is logged or both, right? In this case, so beta 1 implies that, so when log of x increases by 1 unit, y will increase by beta 1. But 1 unit increase in log of x is 100% increase in x. So this is kind of too much change. So I would say this way. When x increases by 1%, which is more natural measure, natural unit, then y increases by 100th of 100th, right? So 0.01 times beta 1, right? So beta 1 captures 100%, so you have to scale it back down to 1%. When log is taken on y, but x is just usual, then beta 1 captures when the effect of x1 on log of y. So when x1 increases by 1, log of y will increase by beta 1. So when log of y increases by beta 1, that means y itself increases by beta 1 times 100%, because a unit increase is equivalent to 100%. So like if you multiply beta here, you have to multiply beta here, right? Similar, then finally, if both are log, then use 1% and beta percent. It's easy because you have to adjust 100 this way, they cancel out. So in the end, log model will simply 1% to 1 beta percent. Okay, this is how you interpret log model. Finally, interaction term like is this. Multiply two variables, x1 times x2 is included, right? So up to this point, it is standard linear regression, but we allow their interaction. And then that means this marginal effect will include this term, right? If you differentiate this term, you are going to get this as a derivative. That means the effect of x1 on y is not just beta 1, but plus something that depends on another variable. So x2 will affect, so the effectiveness of x1, the effect of x1 may differ across different values of x2, right? So the effect of your education, college education, will change over your life. Like as you are more experienced in your career, then your college education may realize more, like many years later, something like that. Okay. So anyhow, if I give you the estimate of beta 1 and beta 3, you should be able to calculate the marginal effect. Similarly, here, if I tell you beta 1, then you can interpret that like this, right? Or I can ask you how much y would change when x increases by, like, say, 10%, right? Then with beta 1, you can calculate that. And similarly, if you know beta 1 and beta 2 estimate, you can calculate the marginal effect. Okay, and then the next topic, panel data. Idea is pretty simple, right? So basically, we have additional structure over time. So we not just observe people, but we observe the same people over time. Then in the end, we include these two fixed effects, right? So we call them two-way fixed effects model. Like these are the same linear regression part. Then the interpretation main point here is alpha I, which depends only on I, that is the point. T does not appear here. So this is specific to the individual, but do not change over time, does not depend on T. So over time, this is the same, but fixed over time, but different across people. So it includes anything. You can put anything into alpha I as long as the omitted variable does not change over time. Similarly, lambda t depends only on t. I does not appear here. That means this is time fixed effect. This controls for any effects that are common to everyone because it does not depend on I. Same for everyone, but specific in a certain time, right? Like COVID, effect of COVID. It was worldwide, but at the same time, but to everyone. So like if you do not include these guys, basically they are kind of omitted variable. All right, controlling for the omitted variable. So without including the fixed effect, the signs could be different. So you have to correctly interpret the the beta after including the fixed effects. Or without the fixed effects, if you find wrong like signs here, then you may guess there should be some omitted variables, right? Okay, the next chapter, binary dependent variable. Like when y is binary, binary means of course 0 or 1, right? If a variable outcome is binary, yes or no, like that, then first it is pretty easy to show that expectation of y equals probability of 1. I I give this equality because you this interpretation is unnatural in many cases. Because yes or no, if you think about yes or no, there is no average of them. Yes or no has no average between them. So I would interpret this way. What is the probability of yes? Okay. Then the simplest method is to use the linear regression, which is specifically called linear probability model because probability is assumed to be linear, right? Basically, there is no, it is exactly the same linear regression with different interpretation using binary structure, okay, because we got probability. But just like everything is the same, but you just interpret the prediction as a probability. The problem is your predicted value can be negative or greater than 1, which a probability cannot be. Um, so how to solve that, resolve that? We put another function here, right? We keep the linear part as usual, but we impose something else in front of that. So this is a nonlinear function that makes the value between 0 and 1, right? So that the result is a probability. Most common function is probit or logit. So the most common model based on this idea is probit or logit, depending on the choice of link function. We call this link function. Anyhow, depending on what kind of function you use in here, we call that either probit or logit, or you can think about different types of models, but these two are the most common ones. The problem is because you have another step of manipulation, beta 1 does not have a meaning itself, right? There is no direct interpretation for this, no economic interpretation for beta itself. So I recommend you calculate the marginal effect, which is derivative, but because if you differentiate this part, but because of this nonlinear function, its derivative remains after derivation, like differentiation, right? So beta is multiplied by something else. So without this adjustment, beta means nothing. You have to be careful when you interpret this idea. Final chapter, the instrumental variable. In the big picture, endogeneity problem is the title for the problem, the most generally defined name of the problem, and it is the regressor correlated with an error. So earlier in the one of the assumptions for the regression was that the regressors must be uncorrelated with the error term. But if they are correlated, we call that endogeneity problem. And examples include omitted variable bias or simultaneous causality, like supply and demand, price and quantity, right? Supply and demand, they are simultaneously determined. And price and quantity, if you affect one of them, then new equilibrium is more complicatedly uh, defined. So, and the problem is we would like to randomize X. We need randomize X, independent randomization, controlled randomization in X, but that is not possible because it's correlated with error. When you change X, error will follow. So then our idea is let's find something else that is outside of the model, but you can randomize it, right? That is instrumental variable Z. This is a very smart idea, originated from economics, not in, not out like, and exported to statistics, right? So then this should satisfy this. First, Z itself must be uncorrelated with the error, which means you can randomize it. Z can be randomized, but it must affect or correlated with X, right? So Z will affect X because it is an indirect randomization instead of randomization on X, right? So for the randomization help, you find the effect of X, it should be correlated with X. Then the intuition is like this. The effect, when you change Z, the instrument, and then you can see the effect of Z on the outcome Y. But the idea is this effect is transmitted from Z to X and then X to Y, right? And from the data, you know this total effect from Z to Y, and you observe this effect, Z to X. And this is what you want. You want to estimate the effect of X on Z, but you know everything else. You know the total effect, you know effect of Z on X. Then you can recover the missing portion, right? So that idea is called two-stage least squares, right? Calculating this, and then in the end you get the in the middle, right? So you don't need to know how to do it, but just the idea. I think the idea is more important. Idea is more important, and the endogeneity is more important. This is pretty common in almost any kind of economics data. Okay, this is a brief review of a semester. I hope this helps, and see you in the final exam.